So last time we saw that we drew these pictures for SO3 and SU2. And the pictures were that SO3 is a ball of radius pi, and psychologically we can draw SU2 of double the size, although remember there is really no size in this space. And these are the directions tau x, tau y, tau z, or tau 1, tau 2, tau 3 I think, but whatever. So this, and you can erect your n cap here, or somewhere here, wherever. And the expressions here were exponent of, if you put j, then you put I also, I n cap theta, n cap dot j times theta. Okay. So e raised to I theta n cap dot j. So this always reminds me of Euler's theorem that every rotation is ultimately a rotation about some one axis. So there is an n cap. So you can do all kinds of rotations, but the beginning position and the final one are always connected by a single rotation, which is a rotation about one axis. Okay. Composition of any rotations is a net rotation theta times n cap dot j. So n cap is the axis of rotation, theta is the angle of rotation. So totally there are exactly 3 parameters connecting any one orientation of body to any other, even when it has gone through all kinds of complicated paths. So this is what I would like to call it's part of the Euler's theorem. And we saw that this theta goes from, theta belongs to, and let us write it as 0 to pi. Okay. And there is the whole question, so it is 0 to pi like this. But we will say more about that in a little bit. On this side we have exponent I times theta times theta times n cap times tau, n cap dot tau by 2. So either you put 2 under the theta, which is often done, but to remind you that in group theory sense it is tau by 2 which is the generator, you should put half there, but the net consequence is the same. So this is u n cap of theta, and this is what we called r n cap of theta, rotation, that is u n cap of theta. And the interesting point is that any n cap of 2 pi becomes equal to minus 1, because this has expansion cos theta by 2 plus I n cap dot theta sigma times sin theta by 2. So when theta becomes equal to 2 pi, you get cosine of pi, so you get a minus sign in front of the identity matrix. And whereas here you get either plus pi, or if you flip the n cap to minus n cap, you are basically doing the opposite rotation. So you cover the distance from minus pi to pi by choosing the n cap appropriately, but it never reaches minus 1. It does so. Okay, so the outermost point of this are all independent, but the opposite points are identified. So now we are coming to the topology part of it, which is that, so in SO3 we at theta equal to pi, we can take, I will just leave this side for SU2 statements. We can let theta go from 0 to 2 pi, but then n cap pointing in only half of the hemisphere are required. In one hemisphere. Suffice. Right? This is an important statement. This is the important statement. So suppose I take the hemisphere corresponding to the upper bowl, which is right. So the one defined by Jx Jy plane. And suppose we take only all the n caps pointing in this and not go below, but we go 0 to 2 pi, then we have covered all the rotations. Or we can go 0 to pi and then take minus n cap as well, opposite all of the n caps, but then only restrict ourselves to go from 0 so sorry, either I take one hemisphere and 0 to 2 pi, all of the possible rotations, so I come back to the original, but then there is no point taking the other side, because the same orientation I can obtain by doing the larger rotation here, or I restrict myself to or let n cap vary over all angles, all directions, but restrict theta to belong to 0 to pi. And now I will draw a dotted line here. The point is that if I do a pi rotation, so if I do a pi rotation about this direction, so let us look at this diagram. If I do a pi rotation, I reach this point. So as you know, in this diagram, theta is the magnitude that by which you scale this n cap vector, because theta multiplies the n cap vector. So theta is the magnitude of the vector. So the amount of rotation is given by the magnitude. So when I reach here, I have rotated by exactly pi. So I have done this rotation. But to go to further, greater than pi, I am supposed to now start the other way and reach that point by using minus n cap. So I can reach this point, but if I now start off with the opposite direction n cap, minus n cap, then I will be double counting if I reach the opposite, this point. Okay. So n cap are unit vectors, and the amount of rotation is how far you go in this. Okay, so this is theta. Now let us draw a physical space picture. Let us take a cube, let us say. A cube is, I don't know whether what to take, actually not a cube, cube is not a good idea. So suppose you take a slightly uneven shape and you rotate by pi, then this point comes here and you get the, the corresponding opposite shape. If you want to rotate further, so this is pi rotation. If you want to rotate further, either you can keep rotating further up to 2 pi, which is this choice, or you can say if you want to reach, so suppose this is a, some p, vector p. Suppose I want p to be here, p to reach here. I can either rotate by this way, or I can now start rotating in the opposite direction, which, so I should have, this is what I should have emphasized. The theta rotation is always entirely counterclockwise, looking down on n cap. Okay, that's our usual convention. So with that convention, if you now want to reach this, you can also reach it. So either by rotating counterclockwise this way, or by taking minus n cap and rotating counterclockwise this way. So you can reach this point in SO3 in two different ways, either like this or like this. So this is the case 1, and this corresponds to this choice, the lower choice, sorry, okay, where you let n cap go only go over all directions. So here you choose, this happens using minus n cap. Minus n cap and counterclockwise from looking from below. So either I use minus n cap, but then I have to restrict to 0 to pi only, because this reaches up to here and this minus n cap can reach up to that. So I have to restrict my rotation angles to theta to pi, and the point is that the actual point pi is double counted in this method, because either you can reach it by pi rotation by n cap or by pi rotation by minus n cap. Therefore, in this picture, these 2 points, the antipodal points on the surface, are actually one and the same, but they are not, they are different, but this point is distinct from, say, this point. So this point has an antipodal point here. So this point is same as this point is same as this point. So now the space of SO3 rotations is the set of points which are inside this ball, some n cap, some size theta, and when you reach the boundary of the ball, you can include only half of the surface of the ball, because the antipodal points are already have to be excluded on the outer surface. So SO3, so with this is the standard choice. But of course the topology will remain same, even if you, that we can argue separately. So if you make the standard choice, then SO3 is the manifold which is essentially a continuum set which can be in 1-to-1 correspondence with R3. Is the manifold of all points, all the points inside the ball. So we avoid the word sphere, because sphere sometimes means only the shell. So to be specific, mathematicians call the full filled sphere the ball. So all the points inside the ball of radius pi with antipodal points on the surface identified, mutually identified. Okay. This is the key fact about SO3. Now you can also, as an exercise in thinking, think of the other convention where you take the upper convention. I will let n caps be only in the upper hemisphere, but I will let my sphere go to size 2 pi instead of pi. If I do this, then again I have going up to 2 pi, but then the outermost points are all included now, except that on the the great circle on the hemisphere, I can take only half of the points, because again the antipodal points are there. So remember that when I take this and when we said we identified antipodal points, it means that I have to leave out the outermost peel or outermost shell of this lower half out. Not only that, on the equator I can take only half of the equator. Not only that, I can only take the semi-closed equator, include the point 0 but leave out the point pi, because pi and 0 are also identified. So it is a slightly strange manifold in which the outer surface is only half of it is there. But the rotations that are about along this direction remain independent of rotations around this direction, because when I reach pi by using this axis, it is different from having reached pi by using some other axis. So the configuration may look similar, but you can never actually continuously deform this pi rotation to that pi rotation. So they are actually, although antipodal points are identified, this point remains distinct from that point. So suppose we call this A and B, and A prime and B prime. So A prime and B prime I will write over here. Here I have not been so careful, so let's put it again. So let us say there is A and B, and I have A prime and whatever I am drawing here, wiggle B prime. So A prime is same as A, B prime is same as B, but A is not same as, in any group theory sense, A and B are distinct. Now we come to SU2. SU2 story is a bit simpler and nicer, because SU2 simply says take n cap and let theta go from 0 to 2 pi. And actually there is no harm including the 2 pi. Okay. Because when it reaches 2 pi, it becomes -1 in the group. So regardless of which direction you reach that -1, it is -1. And in SU2 case, the entire outer surface of the ball is 1 point, topologically 1 point, one and the same point. and the surface theta equal to 2 pi with u of 2 pi regardless of whatever n cap is equal to -1 is is 1 point. So now what happens is that the difference between SO3 and SU2 is that in SU2 the range of parameter is double. Okay. If you take the standard choice n cap varying over the whole sphere, then you have to restrict theta to go from 0 to pi, aside from all the fine print about what happens at the surface. So, but it goes 0 to pi, whereas in SU2 it goes from 0 to 2 pi, and only when you reach 4 pi do you get. So if you do this convention for SU2, take only upper hemisphere, then you can go all the way to 4 pi, and then you will return to +1. That is expressed simply by saying that you can go to -1 from any of the directions. But the size of this, or you can say there is a 2 to 1 mapping from SO3 to SU2. Two to one homomorphism from SU2 into SO3. Then we finally come to the most important topological property. Therefore, SU2 is a simply connected space. Every single curve in SU2 can be shrunk to a point, but in SO3 you cannot. Whereas SU2 is simply connected. Once it is simply connected, it is automatically connected. Connected means any 2 points can be joined, okay, by a arc within the set. But it is not simply connected, which we will just check, which I will prove in a minute. Whereas SU2 we will find is simply connected. Now remember, the definition of simply connected is that every single closed curve can be shrunk to a point, and not simply connected means there exist loops that cannot be shrunk to a point, but there will be an equivalence class of them. There will be a whole, so there basically they will fall into two equivalent classes in the case of SO3. Either they can be one class which can all be shrunk to the origin, the other class which cannot be shrunk to the origin. And the picturization goes as follows. If you take SU2, which is easier to explain, think of one class of loops which are entirely inside. Okay. You can always shrink this to a point, no big deal. Right. So this can be shrunk to a point. Take another class of loops which start somewhere in the interior, then reach the boundary, but now boundary is all 1 point. So I can re-enter through here. So I go like this. Remember, actually this is a little bit confusing because this is not a rotation, this is a sequence of many different rotations. So we are in the space of all possible rotations, but there is a path in this space, it goes here. I can re-enter through this point. So I can magically come out of that and re-enter through here, because they are actually one and the same point, and then I come and close the loop. Okay. Because the whole thing is -1, it's just -1. Therefore, I can continue by coming in from any other point, but these points are after all one and the same. So there is no harm in slowly sequentially converting it into nothing stops me from doing this, and finally I make this. So the path P1 and path P2. So we can define a path P as a function of t such that well, that's actually not the argument. The argument is that I can shift this point indefinitely to there, then it becomes a closed. So P of t such that P1 can be smoothly dragged to P2. And once it reaches, once the outermost point reaches here, that has now become a closed loop. So I can shrink, it becomes of this class, so I can shrink it to 0. So every single point that, every single closed curve you can imagine in this space is shrinkable to a point. But SO3 is not like that. Now in this case, if I start like this, I reach, let us say, this point. Now according to rule, if I want to continue, I can continue only from the antipodal point. I cannot re-enter from any other arbitrary point. So I can re-enter through an antipodal point, and then I continue, come to the beginning point. So of course here also there are the trivial class of loops which are just closed like that. But there is this class of loop which is a closed loop. Now you can see that this cannot be shrunk to a point. The reason is that here when I shifted this point along the surface, I was just sitting at -1, -1, -1 regardless where it appears in this 3D, in this 2D picture. But here the moment I try to shift this point will also shift, because the antipodal points are tied to each other. Okay. So I cannot start shifting these 2 points close to each other. So this class of curves remains unshrinkable. Are unshrinkable. Actually, if it refers to class, then okay, is class of unshrinkable points. is the class of unshrinkable points, curves. So it is like being on a torus or in an annular region. You take the xy plane, but you have cut out some central disk, or even just remove the origin. Then you cannot close the loops to one point. There is one class of loops which don't go around the origin, and the class of loops that goes around the origin. So the same thing happens here. And therefore, SO3 and SU2 are fundamentally different. First we said that this is a double cover of this. But now what we know is that this set is simply connected. So if I embed this SO3 inside this SU2, then I have a double cover, but which is then simply connected. So this is called a covering group. So breaking the curve is not an option. That is not then of course you can't do much topology. So topology deals with the fact that you do continuous transformations, and they deal with essentially with open sets. Eventually, in some way or some sense, you do always keep falling back on your intuition of the real line, where you have this dense set of points which have the continuum, which form the continuum, and even abstract spaces that do not necessarily have the sense of distance or magnitude that the real line has, the connectivity properties can be similar, which you can study by making a one-to-one map, and that map is precisely what this map is, our page 1 expressions, right. This is the map. So this map maps the numbers nx, ny, nz and theta, and this is because it's a unit vector. There are 2 degrees of freedom here and 1 degree of freedom here. 3 independent real numbers mapped into this matrix, which psychologically is representing a point in this abstract space.